Okay, hello everybody. Let's make a start. Thank you. Loud enough at the back, not too loud at the front? Okay, a little bit loud. No. We're never going to make everybody happy. Okay, thanks. So the fourth lecture is really focusing on a little bit more on water security. So pulling together some of what's been discussed in some of the previous lectures, but really from my perspective, I wanted to take you through four sort of main sections of the talk. The first, going back to the big picture and actually explaining how global warming itself affects the global hydrological cycle, because we haven't really covered that yet. And then drill in from there into then how it might affect the hydrology or water resources in a particular water resource catchment. I want to talk very briefly about water security, how it's defined, because that helps us think about water security in the context of Cape Town. And then finally dig down in a bit more detail into Cape Town and really look at the water supply side of it, so water supply security and climate change and what climate change means for security of supply, recognizing that there's a lot that can happen on the demand management side, and that is part of the adaptation response to climate change, and I'm happy to talk about that in discussion afterwards, and fortunately have Helen at the back again, who can also help me on the demand side. Okay, so if we think about global warming or greenhouse gas forcing of climate, what we get, we've sort of been through that stage in the first lecture, but what happens to the hydrological cycle as the globe warms? And there are two main things that happen. We get a warmer surface, which means that at the surface there's more energy available for evaporation. So let me give you an example. Essentially, if you're thinking about a pond of water and it's at close to zero versus at 30 degrees, the molecules of water in that pond have a lot more energy if they're at 30 degrees. So their ability to essentially jump away from the water and become vapor is much easier. So as you're warming the surface, either the land surface and soil moisture, or you're warming the ocean surface, it becomes easier to evaporate water for a given amount of incoming solar energy, essentially. So the water becomes more evaporable. And at the same time, as we warm the atmosphere, I don't know if you remember, one of the graphs I showed in the first lecture showed the increasing trend in this thing called specific humidity, which is essentially the amount of water vapor in the atmosphere. And it's been increasing over the last 50 years. And that's really because a warmer atmosphere has a greater water holding capacity. And that's due to a really nice, simple relationship called the Clausius-Clapeyron relationship that says for every unit increase in air temperature, the water holding capacity of the air increases in what we call an exponential rate. So you warm by 1 degree, it increases by a certain percent. You warm by a further degree, the water holding capacity increases even more. So then you have these two things working together here to actually more evaporation at the surface and an atmosphere that can hold more water. And that essentially leads to more rainfall at a global scale. The average lifetime of a molecule of evaporated water in the atmosphere is something between 7 and 14 days. So when you speed up the rates of evaporation, what goes up must come down, and so you speed up the rates of rainfall. And then when we think about what that means on the land surface, what we call terrestrial hydrology, so the hydrology of the land surface, what we need to be looking at is how these two things play out in tandem. So the land surface, because it's getting warmer, is going to be evaporating more, and at the same time there's going to be a change in rainfall. And it's the balance between the change in rainfall and the change in evaporation that sort of leaves you with how much water there is in a river catchment or a lake. And if evaporation exceeds the change in evaporation is larger than the change in rainfall, you'll have a drier catchment, and the reverse if evaporation is less than the change in rainfall. So hydrologists have this very simple equation which is called the catchment water balance equation, and this really summarizes the water availability or the water resource of a river catchment. like the Berg River, or one of the small mountain catchments on the Cape Peninsula. So Q is a standard sort of physics measure for a flux or a flow. Here we're talking about river flow coming out of the catchment. So Q is the flow, and it's a function of P, your precipitation going into the catchment. So in South Africa, we can talk about rainfall mostly, but precipitation is both liquid and solid moisture falling out of the atmosphere. So if it was snow, it would be solid. But here we're talking mostly about rainfall. Minus evapotranspiration. So evaporation both through plants, transpiration, and from the bare soil. And then any change in storage. So on a year-to-year basis, maybe the groundwater storage changes a bit, and that will then affect the river flow. So what we end up with here is essentially in any particular river basin or river catchment around the world, the impacts of global climate change will sort of flow through this the change in the global hydrological cycle. But what actually happens in that catchment is around the specifics of how rainfall and evaporation change in that catchment. So if you think about the projections of potential change in rainfall that Chris Jack showed in the second lecture, our best guess is for less rainfall over the Western Cape. And so that P value is going to get smaller, and the Q value is going to get smaller as well, the flow. And the other thing that we know is going to happen is that evaporation is going to increase because we have a warmer climate. So we've got both rainfall and evaporation potentially pushing our Western Cape catchments in the same direction of less river flow. Yeah. It comes down, but generally, because we're a peninsula, most of it comes down miles away. And most of our most of the evaporation itself actually happens over the oceans. So the oceans is 70% of the land surface, and it's totally unrestricted water for evaporation. So most continental rainfall is actually sourced from the oceans. In certain parts of the world, there's some local recycling. So in the Amazon forest, which is very, has high rainfall and is very thickly vegetated, and so there is a lot of local evaporation. About 25% of the total rainfall is actually recycled local evaporation, and 75% comes in from the tropical Atlantic Ocean through the trade winds. In the Western Cape, we're not a big enough landmass for that recycling to have any significant effect.
Sorry, is it worldwide? Is it the zero-sum game?
I'll show you now. This is the worldwide now. Okay, so worldwide, if we took, so one of the problems we have in understanding what's happening with rainfall is we have pretty rubbish measurements over the oceans. Unlike with temperature, where ships have gone out and measured sea surface temperature on a regular basis, for the oceans, ships generally don't measure rainfall. They measure weather conditions, whether it's raining or not, but not the amount of rainfall. So we only have complete global coverage for measuring rainfall from the beginning of the satellite era, which is about 1980. So we only really have 35 years of global records. And as Chris was saying on Tuesday, actually getting accuracy from satellite measures of rainfall is really hard because they're indirect measurements, so we have to calibrate them. And if you don't have observations over the ocean, you've got nothing to calibrate it with. So there's pretty heroic estimation that goes on over the ocean. So what we can do is look at climate models. Because climate models, although they are models and we know that they're not the real thing, they do tell us a little bit about what might happen. And this graph shows the change in global precipitation or rainfall for change in global temperature for a number of different climate models. And what we end up is quite a good relationship. Some models warm faster than others, so they have a greater increase in temperature, but in general there's quite a nice one-to-one relationship showing that global precipitation will increase by about 3% per degree global warming. So the zero-sum game at the global scale is a 3% increase globally. That has to, increases somewhere have to be balanced by decreases elsewhere. And as we know, the distribution of changes is not going to be uniform. In the first lecture, I showed those patterns of dry areas getting drier and wet areas getting wetter. that all adds up to an increase of about 3% globally, but some areas become drier and some become wetter. Now, with terrestrial hydrology, there's a very nice, intriguing complication that's a byproduct of global warming, and that's known as the carbon dioxide fertilization effect. And that, I'll explain how that works. So as we increase carbon dioxide, photosynthesis by plants on the land surface becomes more efficient. Many plants are actually, the limitation to photosynthesis, if there aren't nutrient limitations, is actually the concentration of carbon dioxide in the atmosphere. So if you increase carbon dioxide, it actually makes it easier for photosynthesis to occur within the cells of the plant. And the little openings that draw in carbon dioxide to enable photosynthesis to happen, these stomatal openings in leaves, actually narrow because they don't need to be drawing in as much air to get a given concentration of carbon dioxide. What that then also means is there's a byproduct in terms of transpiration, because evaporation from plants through transpiration is actually a penalty that plants pay for drawing in carbon dioxide. As carbon dioxide flows into the leaf, water is a byproduct of photosynthesis and it flows out. It has other purposes as well in terms of changing the hydraulic gradient in the plant so it can draw water up from below. But if you increase carbon dioxide, the net effect across many experiments, and things vary from plant species to plant species, is that there's less total evaporation from vegetated surfaces. So we've got a slight offsetting effect here, that in vegetated areas, the carbon dioxide fertilization effect is actually increasing the water use efficiency of plants in theory. So there's been a lot of experiments, many of them, or some of them done at Kirstenbosch in what they call CO2 chambers. You get a plant, you seal it off in a chamber, and you can change the levels of carbon dioxide in that plant's local environment, and then you can see how its rates of growth and photosynthesis change. So up until quite recently, this was sort of an experimental result, but we, and by we I mean, I think not me, but other people who work on this, think that they've detected this in large-scale river flows. So this is quite a tricky diagram to describe, but this axis here is basically just saying what's the trend in a particular characteristic of the hydrological cycle. And what we see over global land areas over the last 50 or so years is that precipitation has decreased. It's negative, so it's below that zero line. So if we're thinking of that at sort of the continental scale of that water catchment balance, then if rainfall decreases, we would expect river flow to decrease as well. What these people then did was they ran global hydrological models that took into account the effects of carbon dioxide. And the thing here is that what we actually see in observed river runoff is an increase in runoff. So this is what's been measured in large river basins around the world. If you looked at Africa and you took the Orange and the Tugela and the Zambezi and the changes in river flow in all of those, accounting for changes in human use, so just the natural changes, you end up with an increase in river flow. So that's a bit counterintuitive compared to the decrease in rainfall. So the only way that they can actually explain that is by bringing this carbon dioxide fertilization into this hydrological model. And when you bring that in, you end up with this result. That column with the CO2 underneath it is actually the change in runoff when you include climate and carbon dioxide. And it switches from what we've observed as a negative change into an increase in runoff. So it looks like we may be seeing this fertilization response affecting at large scale water availability. But again, depending on the vegetation and the amount of rainfall change in any particular catchment, whether that effect is enough to offset the change in rainfall will depend on the local conditions. Okay, we're going to start zooming in a little bit to Cape Town now in terms of changes in the hydrological cycle. And I wanted to go back to what Chris had said on Tuesday, which is around our main rainfall producing phenomena are the cold fronts that develop deep in the Southern Ocean, and then flow in those westerly winds, and then the fronts propagate up, and if we're lucky, hit the tip of South Africa and hit the Western Cape. And Chris didn't really show this diagram, but it shows projections for the change in the tracks of those storms, where they tend to occur. And what this graph shows is this is Antarctica here, this big white patch here, and we have Australia here, South America, and South Africa, Southern Africa up there. And everywhere that's blue is showing that the frequency, the number of storm events of frontal systems in that area is decreasing in the future. And everywhere that's red, there's an increase in the frequency. So this really, from a model projection perspective, is showing quite clearly that in this zone, which is the zone that clips the tips of all of these southern hemisphere continents, there's a decrease in the frequency of these frontal systems, and they're becoming more concentrated over the Southern Ocean and around Antarctica. So if we're thinking about water security in Cape Town, this is quite a nice mechanistic explanation for what the models are showing in terms of rainfall changes, because the atmospheric dynamics are leading to fewer rainfall events over the southwestern Cape, and therefore lower rainfall itself.
Excuse me.
Yeah.
That shows a yellow band over the tip of Africa. Up there.
Over there, yeah.
And yellow down below reads number density per month unit area increasing between 0.3 and 0.9.
Yeah.
Am I reading that correctly?
You are reading it correctly. So we may be lucky. I hadn't even noticed that. So well done. So I guess here the question is, whether that yellow actually sits over the Western Cape or whether it's slightly further inland. But it's interesting that it is not as strong a signal as over southern Australia, for instance, where it is a definite decrease. Okay, so I want to just quickly talk now about water security and water scarcity. And in the sort of with the people who work on these sort of water security and water scarcity issues, they generally talk about two types of water scarcity. First order water scarcity, which is where there just isn't simply enough water available to supply demand. The second is second order water scarcity. That's where there's water available, but it's just not being managed or captured and delivered to the people who need it. In many developing country situations outside of South Africa, or if you looked at somewhere like the Eastern Cape, so the Eastern Cape is probably the only part of South Africa where there's excess water flowing in our rivers at the moment, untapped water. But it's one of the areas with the lowest levels of service delivery in South Africa. I think the proportion of people in the Eastern Cape who have piped water in their house is something like 20% or something like that. 25%, very, very. So that's a second order water scarcity issue. There's water there. There just hasn't been the investment in water infrastructure to both capture that water and deliver it to those who need it. Contrast that to the Western Cape. As you'll see, we've got a very sophisticated water resource system. And so here, we really are dealing primarily with first order water security or water scarcity. We've essentially tapped just about every economically viable natural source of water, and that's all been allocated and used, and so we're sitting in this much tougher situation of first order water scarcity. So if we think about scarcity, I wanted to just start off by looking globally at sort of the pattern of water scarcity, and this is just one measure of water scarcity. Essentially what it does is sort of a global standard that if the abstractions of the naturally available water, so all the water that flows in groundwater and in rivers, is above 40% of the total, so 40% of the water is being taken out of rivers, that's when you start heading into water scarcity. And that's partly because this is the average flow in rivers, and in dry years there's going to be lower flow. So 0.4 of the average means a lot in a dry year. So that value is kind of a best estimate of water scarcity. So this is, well, it's a situation about 10 years ago, more than 10 years ago. But what these people have done is they've looked at, they've estimated what the river flow is across all catchments around the world, and divided each of those catchments up into little 50-kilometer boxes, and estimated how many people are in each of those boxes from population data. So what this is showing is and then they estimate what the demand might be for a given population. So everywhere that's blue, the demand of that population, that little 50-kilometer part of the world, is less than 40% of river flow. And everywhere that's red is above 40%, so heading into water stress, if you like. And then the depth of the color tells you how many people are in that situation. So if we look at somewhere like the west of the USA, all those dark red dots saying there's a supply-demand problem, and there are lots of people living there. So it's dark red. Whereas if you went somewhere where it's pink, somewhere in the interior of Australia, for instance, where there's about 1 person per 100 square kilometers or something like that, there's no water, but there's very low population density. So it's still a stress situation, but not so many people affected. So that's sort of one estimate of the global pattern of water scarcity, if you like. And what these people did, which I thought was quite nice, was they then looked into the future and said, how is that scarcity pattern going to change? And they looked at two things. They looked at population changes and how that would sort of change the demand side, and then they looked at climate change and how climate change then changed the supply side of water availability. And what we have here is two scenarios. The bottom one is population change only, no change in climate. So effectively you have large parts of the world under current sort of water use levels, per capita water use levels, going into water stress. Everywhere that's red is where you're moving into a more stressful situation. Where it's green, there's only a slight change, and where it's blue, there's a decrease in stress. So really anywhere that population increases, you head into more stressful situations. The top one combines that population drive on stress with climate change. And you can see there that actually in some areas it does change. So if you look at the western part of the United States, it's kind of a no change situation in stress under current population projections. That's largely because that's a mature population. It's not changing in the future. But there's a projection of slight increases in rainfall in some areas, and that shifts the stress situation towards less stressful situations. And other areas where rainfall is predicted to decrease, then it becomes more stressful. So kind of the take-home message here, which is really interesting if you think about Cape Town's situation, is that climate change, if you look at these global patterns, is pretty much, it's like the straw on the camel's back, if you like. The big driver of water stress is actually population growth, consumption, so how much water people consume. A bit like the analogy that I gave for carbon dioxide emissions. You know, if you have a population that's large, wealthy, and eats lots of food and has swimming pools, then they're going to have a large water footprint. And that's the main driver of water stress going forward, or potential water stress. Climate change just sort of tweaks that situation, if you like. And if you're unlucky enough to be in a location with increasing demand coupled with decreasing water availability, then you have an exacerbated water stress situation. Okay, so let's move on to the Western Cape and Cape Town. So as Chris noted on Tuesday, the Western Cape Town itself water comes from a much bigger system called the Western Cape Water Supply System, or the WCWSS. And essentially how this is managed is we have all of our major dams. So for instance, there's the Theawater Kloof Dam over there, and up top there, the Voelvlei Dam. And they're all linked together through a water pumping and redistribution system. And in theory, the levels of those dams are managed with transfers between them to maximize the yield that is required across the distribution system. So we have, and in Cape Town, we draw from the Palmit, actually pumps water up into the Steenbras Dam and then through into the Cape distribution system, and then all of the Berg River system also feeds into Cape Town. So when we talk about Cape Town, we can't divorce Cape Town from the broader Western Cape supply system, and we particularly can't divorce it from the agricultural economy that is in the Berg River and the Beerde River and the Overberg area, because they are also part of this demand for water. So this is the 2014 water use within the system. So you can see that Cape Town really is the elephant in the room. 66% of the water allocated in 2014 through this water resource system was supplied to Cape Town. And I can't remember the exact figures, but it's something like 60 to 70% of that is to domestic water use. The rest is through to industry, municipal use, golf courses that don't have their own boreholes, etc. So the domestic water use side of it is actually the big factor in terms of water demand in Cape Town. So in 2014, I don't have updated figures. Unfortunately, they probably are floating somewhere in the depths of the city of Cape Town, but they're not easily publicly available. The total use was 507 million liters, so megaliters per year. The allocation to the whole system was 584 megaliters, and the yield, that's what it can, so the total that the system can supply, was 596 megaliters. And that's on a 1 in 50 year yield. What that means is when they model the yield of the system, the hydrologists will look at historical rainfall data and put that through the water resource model, and they will say, we can guarantee, given historical climate variability, that we will not be able to provide that yield 1 in every 50 years. So that's kind of the water resource system failure rate. Once in every 50 years, we should expect demand to exceed supply, or that yield not to work. So Chris showed this diagram on Tuesday, but effectively it shows our water use against what the system can supply. And this is the system as of today, about 600, just under 600 megaliters or million cubic meters per year. And that's with the Berg River Dam that came on stream roughly 10 years ago, whenever it was. And here's the actual water use through to 2014, and different projections of potential demand, depending on different assumptions. They all use the same population growth scenario, but they have two different population growth scenarios, the low growth and the high growth, but then they also have different levels of demand management. So this bottom line is kind of hitting the holy grail of the best that we think that the various practitioners think they can deliver in terms of demand management. So depending on how water use actually trends, at some stage, somewhere around about 2022, that 1 in 50 year security of supply is going to fail, because those demand lines cross over that blue band, and something else, some other supply option is going to have to come into play. And these are the supply options that have been proposed in order of essentially cost or ease of implementation. So the first, which is I believe already happening, is the building up of the level of the Full-Flay Dam, so it can actually store more water for redistribution. After that, there's a plan about the Table Mountain Group Aquifer, and then reuse, so taking water from your sewers, cleaning it and putting it back into the system. Another one of the aquifers, reuse, and then up at the top is desalination. And that really reflects, among other things, the cost per litre of these different augmentation options. So you want to go for the cheapest one first and the most expensive ones later on. And that's particularly the case for desalination, because the the price per litre, the cost per litre of desalination has just been going down and down and down over the last 30 years. And that's because of increases in technology. So the energy efficiency of desalination has probably gone down by about a third. So your energy costs have gone down by a third. And then other factors, basically the yield per unit energy. So the trick here is if you're thinking about desalination, the later you leave it, the cheaper it's going to be to build and install this solution. Okay, so Chris showed this diagram. So this is how that supply side situation changes with what the Department of Water Affairs considers to be a worst case climate change scenario. So worst case climate change scenario is sort of at the low end in terms of, the high end in terms of reductions in rainfall. So essentially what it does is essentially each of these different parts of the water resource system, their yield decreases as climate change progresses because it's getting drier and drier. So what that does is it actually shifts the time that you need to bring in these new supply systems. So without climate change, you would have had to bring in full flay in 2022 or whatever it was. Now it has to be up and running in 2020. And so what's actually happening at the moment, that's why full flay is being is in operation already because of this recognition. So each of these then stacks up to mean that every option has to come in sooner and sooner, which has really big expense and planning options. So it takes a long time to actually do a feasibility study and design and environmental impact assessment of all of these. So it really is putting a big pressure on the design process to bring these in sooner and sooner. So what I wanted to look at now is, are we really heading for that worst case scenario? And I want to look at it in two ways. The first is to look at the last 50 years of rainfall. This is another version of the data that Chris showed on Tuesday. But this is essentially the reason we are in this water stress situation in the Western Cape at the moment is because we've had 2 dry years in succession. So if you look at the reservoir levels, the lowest total reservoir level in 2014, 3 years ago, was higher than the highest level in 2015. And since then, we've been going down. So why we're struggling now is because the dams didn't refill completely in 2015. Then we hit the 2016 winter. You've already got a partially depleted system, another dry season, and then you're deep in the poo, so to speak. So what I wanted to look at first was and so what I've done here, these are actually 2-year rainfall anomalies. So the departure from the long-term average, but averaged over 2 years. So if we look at 2016, that's actually the average of the rainfall at least at Cape Town Airport of the last 2 years. So it's accumulated rainfall over those 2 years. And it's the driest 2-year period on record. So we are looking at a pretty extreme event. And we've got 50 years of record. This is the year where if we're going to fail, if the supply system is going to fail, it's going to fail. So it's actually working to design, if you think about it. This is the 1 in 50-year event. Unfortunately, we happen to be living here when that happens. So it's actually, the system is operating to its design. The question is its design correct? Because it's designed assuming what we call a stationary climate, that climate isn't changing. So if it so happens that those kind of events become more frequent and not just once every 50 years, then the design needs to change. And that's why these new supply systems need to come on tap. So we can actually try and quantify how the risk of an event like that, like this current one, has changed due to greenhouse gas emissions. And this is called climate change attribution. So I better do those so you can see it. Yeah. And so we can actually use analysis techniques to say, has human forcing of climate actually changed the risk of dry years? So has it changed the risk of the year that we're experiencing at the moment? And this is, for those of you who have a medical background, we use something called fractional attributable risk. And I'll explain what that actually means. if you think of a medical experiment, you might be interested to know what the change in risk of dying before you're 60 is if you're a smoker or a non-smoker. Okay, so if you don't smoke, there's a certain probability that you're going to die before you're 60 or 70 or 80. And if you're a smoker, there's a certain probability, a different probability. So you have two experiments. You have a control experiment, and for this particular experiment, you would be going out and tracking people and asking them, have you smoked in your life? And then checking when they die. And then it's kind of a real-world control experiment, because you have both the control and the intervention. So the intervention may be that you smoke, or it might be that you don't smoke. And then you can sample across both of those and look at how the risk changes. So that then leads you to a control and an intervention response, if you like. And in this case, our response is the probability of some impact X. So death in the case of smoking, or maybe just cancer, lung cancer in the case of smoking. But when you look at climate change, our control is climate without greenhouse gases. So the world that would have been if we hadn't spent the last 150 years emitting greenhouse gases into the atmosphere. And then the intervention experiment, if you like, or the forcing experiment, is climate with greenhouse gases, the world we have. Now the problem is we don't have multiple worlds to sample like we do with people who smoke and don't smoke. So we have to disappear into the model world and run climate models with and without the effects of the historic greenhouse gas forcing, and then look at the outputs from the model to see how rainfall over the Western Cape looks if you have a greenhouse gas driven model and a non-greenhouse gas driven model. So you can compare your control and your intervention experiment. So some very preliminary results. I've got a student who's starting to work on this year, but this is a cumulative probability diagram of 2-year rainfall. So it's taken in a anthropogenic or forced climate model run. So this is the output from the climate model over the Western Cape for rainfall. We calculate, just like I did previously, the 2-year average rainfall, and we look at how the change in rainfall over a 2-year period stacks up against probability. And the rainfall event that we're interested in this last year in the model world is about minus 0.575 millimeters per day. And that has a probability of happening with climate change, it says, of somewhere around about 0.025. So quite a small probability, but it is an extreme event. We can then compare that to the same set of results when you add in a unforced climate model run. So the brown curve is what the model thinks would have happened if we hadn't emitted greenhouse gases. So it's a world today without greenhouse gases. And what you can see is that whole curve is lower down. And so essentially what it's saying is the risk of that is changed. The probability of that has changed to something like 0.04. I've got this the wrong way. No, that's the wrong way around, but anyway. So the probability with climate change is 0.04. The probability without climate change is 0.25. I got up top right, those two figures are fixed up. And then you can look at the ratio of those probabilities and come up with the fractional risk change. And so there's a change of about 37%. 37% of the risk of this event happening today is due to climate change. 67% is due to just natural variability. So we can actually start to proportion the changed risk between what would have happened anyway and what climate change, what global warming has added onto that. So what that really means is the forced run is a 0.04, so that's roughly a 1 in 25-year event. And the unforced one, 0.025, that's a 1 in 50-year event. So we've changed the risk of a drought like the one we're experiencing from 1 in every 50 years to 1 in every 25 years, according to the climate models. And we all know climate models must be treated with caution and skepticism, but they hopefully tell us something about the real world. Okay, I wanted to finish off with something that's really important and people often forget, which is also the other... happened there? Okay, yeah, here we go. Which is the other part of the demand on the water resource system, which is what we call the Ecological Reserve. So in the Water Act, the first take on water in our river systems is actually the natural system. And you need to leave a certain amount of water in the system at different times of years for those aquatic ecosystems to operate in a way that supports the natural ecology. So in winter, most rivers in the Western Cape need floodwater coming through because many breeding cycles are triggered by peaks in floodwater. So at the moment, there is no allocation to the Ecological Reserve in the Western Cape water system. They're busy actually at the moment. There's a big study going on determining what that should be. But if it does come in place, at least by law, there's going to have to be some of this current yield is actually going to have to be allocated away from people to letting it flow down the rivers and supporting ecology. And it's the order of 35 million cubic meters per year. That looks like what it's going to be over the whole system. So what we have here then, if you like, in terms of the supply side situation is good environmental stewardship would say we should be using some of that water for the environment, probably climate change coming in and also reducing the flows. So we've got two sort of additional factors that are, these two factors that are pushing, adding stress onto the water resource system that really needs to be taken into account. So I'm going to stop there. I was going to try and show you some projections about how that risk might change in the future, but unfortunately I got food poisoning last night, and so my talk didn't make much progress over the night or over today. So we're going to stop here with the current risk that we're experiencing and what we can attribute to climate change. But I think you would expect that risk would, given the projections we have that Chris showed, would be increasing in the future. So today's drought has become possibly a 1 in 25-year event. In 10 years' time, it might become a 1 in 10-year event. And so we have to plan for that kind of eventuality. Okay, so plenty of time for questions. So yeah, please fire away. I'm going to start at the back this time. Last time I started at the front, and we'll work our way down. So yeah. Okay. Yeah, it's a hardcore hydrological graph, so I'll explain it to you. Just hold on, just ask again while I get it up. So this is, each of these dots, you can see the dots here, they're stacked together closely here, is one data point. And what I've done is I've taken the last 50 years and I've sorted them from small to large. So this one is the driest in the model, and it's sort of, and then you go to the wettest 2-year period up that side. And then what it has along the bottom is the probability. So it's the probability of a value being drier than a certain level. So it's 100% probability that it's going to be drier than the wettest year. And as you go to drier and drier, the probability decreases. So here, the probability of it being below minus 0.5 roughly is about 0.04. So basically, there's no time involved here. It's just a ranking of the years from wet to dry. Yeah.
Could you explain a little bit about using water from the table now to the group?
Yeah.
It had to be quite a major factor, of course. And I presume this is all pumping and borehole extraction.
That's correct. I'm not that familiar with the details, but as I understand it, there are certain areas where the Table Mountain aquifer actually is artesian, so it has pressure that would bring the water to the surface. And I think one of the artesian spots is somewhere in the Overberg area. So if you drill down there, the water's, because of the pressure of the water, because basically the aquifer has got that kind of shape from the mountains around, then the pressure of the water that's coming down into that sort of bottom of the U will force it up automatically. That's an artesian well. So if you can drill into those, then you don't have to pump it out, but then you would have to still pump it across to the Cape system. So there will be electricity charges. If you're trying to tap into it, somewhere within the Western Cape system, I think there will be problems. And then the other is that the Table Mountain Group aquifer is not a particularly good aquifer. I mean, if you think of when you're walking up Table Mountain, those sandstones are pretty damn dense and crystalline. So you're really relying on fractures in that system to carry the water. And so, whereas if you had a very nice sandy, loose aquifer, you're pretty sure of the quality of that aquifer across the whole system. Whereas here, it really depends on on the fracturing across the whole system. That's very hard to estimate. So the estimates about the yield are actually probably, I would say, are really hard to get accurate. So there's probably some water there, and I think Helen would not know more, but I think there's a plan to do test drilling to see what the critical thing you do with groundwater is you'll run a test, and initially you should get a lot of water coming out, but as you start to draw down from the surrounding area, your flows, in a poor aquifer, your flows will decrease very quickly because the water can't flow back to replace what you've pumped out. So those tests are really going to be important in saying what the yield of it is. Yeah, you and then at the back afterwards. Yeah.
One of the reports that came out just before Christmas said that all the aquifers of the world at the rate of depletion current will be empty by the year 2050. And that means that we're using our children's heritage like we do with everything else. But my question to you is, isn't that also going to affect trees? Because I know that there's capillary action up from the bottom all the time, which the bigger trees are drawing on all the time. I'm worried that per se is also going to affect everything.
Yeah. So okay. So there's two things there. One is what we would call the sustainable use of an aquifer, and effectively over a long time, the rainfall that's coming in wherever the aquifer is at the surface has to match what you pump out. So you can use groundwater systems sustainably. What's happening at the moment in many aquifers is that the rate of pumping is exceeding the rate of natural recharge, and then you are heading for crisis. So somewhere like the Ganges Plain, where there's all this small farmers putting in their own boreholes, the water table's gone down by something like 10 meters over the last 20 years, and that's clearly unsustainable.
Apparently it also makes coastal cities subside as sea level rises.
Yeah. So it exacerbates that. In terms of plants, the kind of aquifers that we're talking about are generally even shallow aquifers, like less so with shallow aquifers, but if you use shallow aquifers properly, so ones that are like 10 meters down, that's generally below the root zone, and so it only becomes important if they really do play a big role in capillary action, moving the water up into the root zone. But the Table Mountain Group is a deep aquifer. It's way below where any roots will get, so it's not really relevant from that point of view. But in places where the Table Mountain aquifer is near the surface, it actually can play an important role in dry season flows in the river. So the water that's coming out, it's sort of maybe come into the aquifer on Snewberg in Wellington, and then trickles down to some place where a river intersects it. That would provide what we call base flow, dry season flow. So if you're pumping from that, it's at the expense of your dry season river flows, which could be important for the ecology. So picking where you abstract the water is quite important as well, just from an ecological perspective. Yeah. So there's a question. Sorry, the gentleman behind you first. Yeah, sure.
The distribution you do there, that's over about 50 years.
Yeah.
You take the 1850 to 1900, 1950, 1950 to 2000. There doesn't seem to be any change in the distribution. So I'm just wondering why during that period it's warmed quite a lot. I can't see any significant change in the precipitation.
Yeah.
That period. By that sort of very self-same.
Yeah. So I think we don't see a big signal at the moment. So I agree with you, and we need to work with longer records, particularly the late 1800s, where we know that there were some significantly dry periods. But what's also quite important is how those dry years are clustered. So you might, I know from the longest temperature record in the world is from central England, goes back to 1690 or early 1700s. The second warmest year in England on record is 1725 or something like that. but the next 9 warmest years are in the last 15 years. So you do get extremes, and what we would expect, what climate science will tell us, is that we start to get those extremes clustered more together. But the problem with rainfall is it's an inherently variable phenomenon on interannual through to multi-decadal timescales. So it takes much longer to pick out a climate change signal. And these results are from one climate model. I deliberately picked one that showed a drying trend over the Western Cape. If we're going to do this robustly, we would need to analyze all climate models and look at how that result changes when you use the full spectrum of climate models. So the lady there, and then the gentleman there.
You mentioned golf courses. One day, conversing with somebody who has a lot to do with golf courses and maintenance, he said that a while back, a number of years back, the golf courses in the Cape would change in days of plentiful water, changed from here, which is our endemic grass, to coquille, with very bad effects to the
Yeah.
water
Mhm. I don't know the details about that, but if a fast-growing, vigorous plant, whether it's a grass, will use more water. Yeah. So, yeah. Yeah. So.
Tell us what the chances are of having another 20 or 50 drought next year.
With some further analysis, not right now, but we can have a conditional probability of having.
The year after.
Yeah, we can work out what we call conditional probabilities.
We're
Yeah.
very close to not necessarily knowing when next our dams will be full.
Yeah. So if I was the Western Cape Water Systems Manager, I would be, and I don't know if they do this, but I would be looking at the current levels of the dam, and I'd be simulating all possible futures based historically and on climate change data to see what the probability of another bad year is. And then you could actually see what the risks are, and it also probably gives you opportunities to think a bit more proactively in terms of earlier water demand measures rather than waiting until it's so obvious that then, I think there's always a problem with being a public official and trying to make people save water. If they don't think that there's a need, then they're not going to be convinced and they won't do it. So when you do have a crisis, then people start waking up and possibly do that. But if you could come up with these projections and say, given the current state, a normal year would be fine, but actually the risk of really having another year is 75%, then that might actually allow you to start planning further in advance. Yeah.
You mentioned the effect of vegetation. I would expect trees to make a much bigger one. Now, what would, in your opinion, would happen if we would increase our forests by 20%? And I'm talking urban forests as well as surrounding areas. Would that have a material impact?
It would have an effect. There's a whole lot of things that happen there. Trees themselves have a very, very low reflectivity compared to grass or bare ground. So you're changing the heat balance of your area and possibly reducing the energy available for evaporation. But trees themselves evaporate about 3 times more than grass or pasture. So in general, trees are bad for evaporation and water resources. Yeah, that's the kind of. There are more water efficient trees and less water efficient trees. You definitely don't want to plant eucalyptus because eucalyptus just pump water out and then they fall over when there's no water left, whereas other trees will slowly reduce their evaporation as they start to get water stressed. So it's a bit like water sensitive gardening. There are water sensitive trees as well, and I'm guessing for the Western Cape, the trees that are that occur. Okay, I'm not an ecologist, but just thinking about it, your montane forest trees typically occurring in areas where there's always water available. So when you're walking up Kirstenbosch, those trees are pretty much never water stressed, but what you want are the trees that are not quite riverine, but close to river and are probably seasonally deciduous, because then they can cope with water stress and will shut down and won't. So if you, yeah.
That's a view that's only held really in South Africa, because elsewhere they consider that trees are natural pumps and that they actually control the flow of water into the water courses, and it's mistaken for drinking the water.
No, I think you're taking. There are two views, even globally, about that. Forests, well, good landscape management will enhance the soil moisture holding quality of the soil. Forests do that, but other types of landscape, you can also do that. And if you look at the evidence from around the world, there's long experimental evidence that shows that on average, trees, the evaporation from trees outweighs their sponge characteristics.
But Israel increased its rainfall by 10%, by 20%, by just increasing the number of trees by 22 million.
I'd like to see that paper, but because that's at odds with a lot of with most of the systematic studies that have looked at this across multiple experimental sites. Yeah, so where it can make a difference, and so there's been, again, not because we don't want to go and deforest huge parts of the Amazon, but if you simulate removing huge parts of the Amazon, because the Amazon is so big and the recycling effect, then you do stimulate water, do stimulate more rainfall. You take them away, Amazon rainfall decreases because you're losing that recycling capability. So I'm quite surprised about Israel, because normally the effects of afforestation have to be at a scale that actually makes a difference to internal recycling, and that has to be quite a large scale. But yeah.
You showed that full flow would be Cape Town's next water supply system.
Let's check. Helen, is full flow the next one coming on the tap? Do you know? It is the one that was planned. I just don't know what decision has been made. So that was the plan. Yeah.
And it's off channel, and it gets water from brought in by canals from 24 rivers in Clanburg.
Yeah.
So where will the next water come from? The Breda or the Berg River?
The next one there is the aquifer. I mean,
no, the water that's, if they're going to make full flow bigger,
yeah.
First of all, the canals would be at the wrong level, but where would that additional water be coming from?
From the same system, so there'd just be less flowing down into the lower berg. Effectively.
The present canals are dry because they bring the water in winter, so where would they bring them from with additional capacity?
I'm guessing that not all the water that could be abstracted from these sources is currently being abstracted. I mean, I don't know the details, so there would be more water would be flowing down those canals when it can be abstracted from the different sources, with obviously impacts elsewhere downstream of those sources. It's a zero-sum game, as somebody said somewhere. Yeah, sorry. Okay. Couple more questions, and then we'll call it a day.
Doesn't the whole exercise actually become pretty academic? Because the fact we have to face, our population is growing, our demand for water is going to grow. We have to find new water resources. Whether climate change causes a slight fall off in the amount of water flowing into the dams, but that is an academic argument over which I'm not going to get into. But we're going to have to look at reuse of water.
Yep.
We're going to have to look at desalination. We're going to have to look at water transfers.
Yep.
Maybe even from the mouth of the Congo River if we want to get really serious about it. But this is academic in relation to the desperate need of people moving into the cities, demanding water, and it has to be supplied.
So I think Helen gave the best answer yesterday, where she said, yes, these things are going to happen. There is going to be need for, so if Cape Town's population doubles, you're going to have to find the water somewhere. But what climate change does is it changes the timescale in which you're going to have to act. So we could have waited 2 or 3 years before the first augmentation system came in. Now it's bringing it forward in time. So it doesn't change the big picture. And as I said right at the beginning,